Hey there, welcome to another deep dive. Today, we're tackling this research on bias in large language models. You know, those AI systems that can write like Shakespeare or debate philosophy like a seasoned professor.
Indeed. LLMs are fascinating, but their increasing influence makes understanding their potential for bias absolutely critical,
Yep.
especially for folks like you working at the cutting edge of this technology.
Okay, so you sent over this research, and it seems like bias in these models isn't just a simple bad data in, bad data out problem. There's a lot more nuance here, right?
You're absolutely right. The paper distinguishes between intrinsic and extrinsic bias.
Okay.
Intrinsic bias is essentially baked into the model during training, reflecting the biases present in the massive data sets they learn from.
So like inheriting traits from your parents, the LLM inherits the biases from its data parents.
That's a great analogy. Think about gender stereotypes. If the bulk of an LLM's training data portrays doctors as male, it might struggle to process information about female doctors accurately.
That makes sense.
Yeah.
So what about extrinsic bias? How's that different?
Extrinsic bias emerges when the LLM is applied to specific tasks. The same LLM might exhibit bias in sentiment analysis, but not in translation. Depending on the nature of the task and the data it's processing, it's like how human behavior can change depending on the situation.
Interesting. The paper dives into several sources of intrinsic bias. One that really stood out to me was data imbalance. Could you elaborate on how this impacts the model?
Certainly. Data imbalance refers to the overrepresentation or underrepresentation of certain groups in the training data.
Got it.
For example, if a data set primarily consists of text from Western cultures, the resulting LLM might struggle to understand nuances in Eastern languages or cultural contexts.
So it's not just about having like enough data, but ensuring that the data reflects the diversity of the real world.
Precisely. And this imbalance can stem from various factors,
Huh.
including the geographic location and time period the data is collected from. The paper refers to these as spatial and temporal biases.
Okay, it makes sense. An LM trained on news articles from the 1950s will likely have a very different understanding of gender roles compared to one trained on contemporary text.
Exactly. That's temporal bias in action. Similarly, an LMM trained mainly on British English texts might misinterpret certain slang or colloquialisms commonly used in American English.
It's fascinating how seemingly subtle differences in data can have such a profound impact on the model's understanding.
Indeed. And it's not just the content of the data that matters, but also the methods used for data collection. The paper explores how different sources, like scraping web forums versus curated book collections, can introduce unique biases.
Could you give us an example of how the source of the data can impact the model's bias?
Let's imagine an LLM trained heavily on data from social media platforms.
Okay.
While social media can offer a wealth of information, it also tends to amplify extreme opinions and potentially contain more misinformation compared to, say, a data set of peer-reviewed scientific articles.
So an LLM trained on social media data might be more prone to generating output that reflects those extreme viewpoints, or potentially even spread misinformation.
That's the risk, and that's why understanding the source and collection methods of the training data is crucial for understanding the potential biases embedded within an LLM. It's like knowing the history of ingredients before you bake a cake. Each ingredient contributes its own flavor and texture to the final product.
That's a great way to put it. It seems like every step of the data pipeline, from collection to curation, can introduce or amplify biases.
You're absolutely right. And this complexity is further compounded by the inherent ambiguity of human language, which even humans sometimes struggle to interpret accurately.
The paper mentioned that even something as seemingly neutral as gender-neutral pronouns can be skewed towards one gender over another based on patterns in the data. That was pretty surprising.
Yes, it highlights how subtle these biases can be. Sarcasm, figures of speech, cultural idioms, all of these can be difficult for LLMs to grasp, and misinterpretations can lead to biased outcomes in their output.
It's like those times when AI chatbots go hilariously off the rails because they miss the nuances of human communication. But it's not so funny when those misinterpretations impact real-world decisions.
Exactly. That's why understanding the differences between how bias manifests in natural language understanding, or NLU tasks, versus natural language generation, or NLG tasks, is crucial.
Right, so NLU is about the LLM understanding language, while NLG is about it generating language.
hmm
Can you walk us through how those two processes could be impacted by bias differently?
Certainly. Let's start with NLU tasks. Imagine an LLM trying to resolve core references in a text, figuring out which pronoun refers to which entity. A classic example of bias here is the doctor equals male, nurse equals female assumption. Even if the text doesn't explicitly state genders, a biased LLM might make assumptions based on societal stereotypes.
It's like the model is filling the blanks with its own preconceived notions, which can lead to some pretty inaccurate interpretations.
Precisely. Now let's consider NLG tasks. Imagine an LLM tasked with writing a story about a CEO. If it's been trained on data that predominantly portrays CEOs as male, it might default to using male pronouns and characteristics.
So even though the prompt is gender neutral, the output ends up reflecting the bias present in the training data.
Exactly. And these biases can have real-world consequences, especially when LLMs are deployed in applications like hiring, loan approvals, or even healthcare diagnostics.
That's a bit unsettling. It seems like identifying and mitigating these biases is crucial for ensuring that LLMs are used responsibly and ethically.
Absolutely, and that's where the paper really shines. It offers a comprehensive overview of various techniques for evaluating and mitigating bias in LLMs.
That sounds like a deep dive in itself. I'm ready to explore those techniques further.
So let's unpack these techniques. The paper smartly breaks them down based on where the bias is being assessed: the data itself, the model after training, or the model's actual output.
That makes sense. It's like a three-pronged approach to tackling bias, starting with the source material.
Exactly. At the data level, one fundamental approach is analyzing the distribution of demographic attributes, things like gender, ethnicity, or socioeconomic status. This helps us identify imbalances or skewness that could lead to biased outcomes.
So, for example, if a data set of news articles primarily features CEOs who are men, that could indicate a gender bias.
Precisely. And it's not just demographics. Analyzing the sources of the data is critical. Is the data scraped from specific social media platforms, collected from academic journals, or pulled from news outlets known for certain political leanings? Understanding the data's origin is key to recognizing potential biases.
It's like considering the soil a plant grows in. Healthy soil, healthy plant. Biased data, potentially biased model. What other tools are there for spotting bias in the data itself?
The paper highlights the analysis of the text itself to detect potentially biased language. This can involve lexical analysis, where we look for specific words or phrases known to carry biased connotations. Think of words that perpetuate stereotypes about certain professions or social groups.
But isn't language context dependent? A word might be neutral in one context and biased in another. How do we address that?
That's where contextual analysis comes in. We go beyond isolated words and examine how language is used within a specific context to uncover more subtle forms of bias. We can also analyze the sentiment associated with different demographic groups or topics within the dataset, looking for negative or positive skews that could signal bias.
So it's not just about flagging specific words, but understanding their meaning and impact within the broader context.
Exactly. But data analysis is just the first step. Once the model is trained, we need methods for evaluating bias within the model itself. Here, we use tools like fairness metrics.
Okay.
These are mathematical measures designed to assess how fair a model's predictions are across different demographic groups.
So if we're using an LLM to predict loan approvals, fairness metrics could tell us whether the model is equally likely to approve loans for qualified applicants, regardless of their gender, race, or other protected characteristics.
Exactly. Metrics like equal opportunity ensure that the model's true positive rate is similar across different groups. Another key metric is predictive parity, which checks whether the model's accuracy is consistent across various demographics.
Those metrics provide a quantitative measure of bias. But how do we understand why a model might be making biased predictions? It's like seeing the symptom without knowing the cause.
That's where interpretability tools come in. These tools allow us to peek inside the black box of the model and understand how different features contribute to its decision-making process.
So rather than just seeing the final output, we can trace back the model's reasoning and see if it's relying on biased factors.
Exactly. One tool is SHAP, Shapley Additive Explanations, which identifies the features most influential in a particular prediction. For example, if we're using an LLM for hiring, SHAP could reveal if the model is placing undue weight on factors like gender or race, even if those factors shouldn't be relevant.
That sounds incredibly useful for uncovering hidden biases. What other interpretability tools are commonly used?
Another one is LIME, Local Interpretable Model Agnostic Explanations, which provides localized approximations of the model's behavior. This means we can see how the model makes decisions for specific individuals or cases, rather than just looking at overall statistics.
So we can check if the model is consistently treating certain demographics differently, even if the overall fairness metrics seem okay.
Precisely. And then there's counterfactual fairness, which asks, what would the model predict if we changed a sensitive attribute, like gender or race?
So we create hypothetical scenarios to see if the model's predictions change based solely on those demographic shifts.
Exactly. This is a powerful way to expose hidden biases that might not be evident through other methods.
It's like a stress test for the model's fairness, pushing it to see if it cracks under pressure.
Great analogy. But remember, evaluating the model itself is only part of the equation. We also need to scrutinize the actual outputs generated by the LLM.
Right. Even if a model seems fair on paper, the text it generates could still contain subtle biases or perpetuate harmful stereotypes. What are some of the techniques used for this output-level evaluation?
One approach is, again, counterfactual testing. Instead of manipulating the input data, we change the prompts given to the LLM and observe how the output changes. This can reveal biases in how the model responds to different demographic cues.
So we could ask the LLM to write a job description once with a male name and once with a female name and see if the language or qualifications subtly change.
Exactly. This helps us identify if the model is subconsciously associating certain professions or characteristics with specific genders. We also use techniques like stereotype detection, where we specifically look for harmful stereotypes in the generated text, and sentiment analysis, which helps us identify biases in the emotional tone of the LLM's outputs.
It seems like a lot of these techniques overlap across different levels of evaluation data, model, and output.
You're right. The lines between these stages can be blurry. And often the most effective approach involves a combination of techniques applied across all levels. Think of it as a web of interconnected checks and balances.
This is all incredibly important work, but it also sounds very technical and complex. What role does human judgment play in all of this?
Human judgment is crucial. Even the most sophisticated tools can miss certain nuances and context-dependent biases.
So we still need human experts to review the model's outputs and ensure they align with ethical standards.
Absolutely. That's where qualitative research methods like interviews or focus groups can also be valuable. We can gather feedback from diverse communities to understand how they perceive the LLM's behavior and identify potential biases that might not be apparent through purely quantitative methods.
It sounds like a comprehensive approach to bias evaluation involves a blend of robust technology and insightful human judgment.
Precisely. But evaluating bias is only half the battle. We also need effective strategies for mitigating those biases. The paper provides a helpful framework for thinking about bias mitigation, categorizing approaches into three main buckets: pre-model, intra-model, and post-model.
Okay, those terms sound intriguing. Let's break down each of these categories, starting with pre-model debiasing. What does that involve?
Pre-model debiasing focuses on addressing bias before the model is even trained, essentially ensuring that the training data itself is as unbiased as possible.
So before we even start building the house, we're making sure we're using high-quality, unbiased materials.
That's a great way to put it. One of the most common techniques here is counterfactual data augmentation, or CDA.
Wait, isn't that the same technique we discussed earlier for testing for bias?
It is, but here we're using counterfactuals to actually mitigate bias in the data. Instead of just asking what if, we're actually generating those what-if scenarios to balance the data.
So for example, if our training data primarily features male CEOs, we might use CDA to create additional examples with female CEOs, thus reducing the gender bias.
Exactly. We're injecting the data with a healthy dose of diversity and counterexamples to challenge the model's potential biases.
That's clever. And are there other pre-model techniques for debiasing the training data?
Absolutely. Resampling the data to ensure a more balanced representation of different demographic groups is another common approach. We can also use expert intervention to identify and correct biased examples within the dataset.
So it's a combination of automated techniques and human oversight to create a more equitable foundation for the model. What about techniques used during the training process itself? What does intra-model debiasing entail?
Intra-model debiasing focuses on tweaking the model's architecture or the training process itself to minimize bias. This can involve incorporating specialized loss functions that penalize the model for making biased predictions, or adding fairness constraints directly into the model's learning objectives.
So it's like building a safeguard into the model's learning process, a kind of ethical compass that steers it away from biased outcomes.
Precisely. There are some fascinating techniques being developed in this area. For example, equalization and declustering aims to mitigate both explicit and implicit biases.
What's the difference between those two types of bias?
Explicit bias is when the model directly associates a sensitive attribute, like gender, with a specific outcome. Implicit bias is trickier. It's when the model picks up on hidden correlations in the data that perpetuate stereotypes, even if those stereotypes aren't explicitly stated.
So equalization and declustering helps the model unlearn both those overt and subtle forms of bias.
That's the goal. Another technique, movement pruning, involves identifying and removing parts of the model itself that are contributing to biased outcomes.
Wow, that's like doing surgery on the model's neural network.
In a sense, yes. We're strategically pruning away the biased parts while preserving the model's accuracy for its intended tasks. It's a delicate balance.
This is fascinating stuff. Are there other techniques for intra-model debiasing we should know about?
There are a few more worth mentioning. Transfer learning, for instance, leverages knowledge from a pre-trained model to improve the performance of a new model, all while taking steps to minimize the transfer of biases.
So we're transferring the good knowledge without passing on the bad biases.
Exactly. And then there's dropout regularization, a technique that helps prevent the model from overfitting the training data, which can sometimes exacerbate existing biases.
It sounds like intra-model debiasing is all about building fairness into the very fabric of the model's architecture and training process.
You got it. But our debiasing journey doesn't end there. We also have techniques that can be applied after the model is trained, known as post-model debiasing.
Ah, so it's like a final layer of protection, a safety net to catch any biases that might have snuck through.
Exactly. One approach is reinforced calibration, which uses reinforcement learning to encourage the model to produce less biased outputs.
So we're essentially training the model to recognize and correct its own biases. That's pretty meta.
Indeed. Another technique is self-debiasing, where we leverage the model's existing knowledge to nudge it towards generating less biased prompts or responses.
It's like the model is becoming more self-aware and learning to police itself.
That's a great way to think about it. And then there are projection-based methods, which involve transforming the model's internal representations to reduce bias. It's a bit more technical, but the idea is to reshape how the model internally understands certain concepts to minimize biased associations.
It's amazing how many tools are being developed to combat bias at every stage of the LLM lifecycle. But with so many options, how do we choose the best approach?
There's no one-size-fits-all solution. The most effective approach will depend on the specific LLM task, the nature of the biases we're trying to address, and the resources available.
So it's a bit like being a doctor, diagnosing the problem and prescribing the most appropriate treatment plan.
That's a great analogy. And sometimes the best approach is a combination of pre-model, intra-model, and post-model techniques, a multi-layered defense system against bias.
It's encouraging to see so much effort going into developing these techniques. But beyond the technical aspects, what are the broader ethical and legal implications of bias in LLMs? After all, these models are increasingly making decisions that impact real people's lives.
You're absolutely right. These aren't just theoretical problems. We're talking about real-world consequences when biased LLMs are used in decision-making systems. The paper highlights the potential for both representational harms and allocational harms.
Okay, let's break those down. What exactly are representational harms?
Representational harms occur when LLMs reinforce negative stereotypes or misrepresent certain groups. Think of an LLM used to generate marketing copy that consistently portrays women in caregiving roles while depicting men in leadership positions.
So it's not just that the output is offensive or insensitive, it's that it can perpetuate those harmful stereotypes and contribute to broader societal biases.
Precisely. These representations can influence how people perceive themselves and others, and they can have a tangible impact on opportunities and outcomes.
It's like the model is adding fuel to the fire of existing prejudices. What about allocational harms? How are those different?
Allocational harms arise when biased LLMs lead to unfair decisions in areas like hiring, lending, or even healthcare. Imagine an LLM-powered hiring tool that consistently ranks male candidates higher than equally qualified female candidates due to biases in the training data.
Or a healthcare AI that misdiagnoses certain conditions more frequently in minority patients because of underrepresentation in the datasets used to train the model.
Exactly. These are scenarios where the LLM's biases directly translate into tangible disadvantages for certain groups, limited access to jobs, financial resources, or even proper medical care.
Those are some serious consequences. The paper also mentions legal ramifications, right?
Yes, this is a critical point. Biased LLMs can run afoul of anti-discrimination laws, leading to legal challenges for companies deploying these systems. For instance, if an LLM-powered loan approval system disproportionately denies loans to applicants from certain racial or ethnic backgrounds, that could be considered discriminatory lending.
It sounds like we're entering uncharted territory, legally speaking. Existing laws may not be adequately equipped to address the complexities of bias in AI.
That's why ongoing discussions about AI regulation are so crucial. We need clear legal frameworks that hold developers and companies accountable for addressing bias in their AI systems.
So where do we go from here? What are the key takeaways for someone working with LLMs like our listeners?
Well, the first takeaway is that bias in LLMs is a complex and multifaceted issue. We've seen how it can creep in at every stage of the LLM lifecycle, from data collection to model training to output generation.
It's not a simple fix the data problem. It requires a comprehensive approach.
Exactly. We need a multi-pronged strategy, utilizing a combination of techniques to evaluate and mitigate bias at every stage. Data level, model level, and output level interventions all play a role in building fairer and more equitable LLMs.
And it's not just about technical solutions. It's about fostering a culture of responsibility and ethical awareness among AI developers and researchers.
Absolutely. We need to prioritize fairness and equity from the very beginning of the development process. This includes having open conversations about potential biases, involving diverse perspectives in the design and testing of these systems, and being transparent about the limitations of these technologies.
And ultimately, it's about recognizing that LLMs are powerful tools that can be used for good or for ill. It's up to us to ensure they are used responsibly and ethically.
Well said. We need to move beyond simply mitigating harms and strive to build LLMs that actively promote fairness, inclusion, and social good.
That's a great point. It's not just about fixing what's broken. It's about using these technologies to create a more just and equitable world. Thanks for joining us on this deep dive into the complexities of bias in LLMs.
It was my pleasure. I hope this conversation helps you navigate this rapidly evolving and increasingly important field.
To our listeners, remember that awareness is the first step towards action. Be critical, be curious, and keep pushing for a future where AI benefits everyone. Until next time, stay curious.